This is a continuation of our lectures on ANOVA. In particular, here we're going to be dealing with the case of ANOVA where you have multiple factors or multiple variables that you're trying to include in the model at the same time. So the key idea here is that the outcome is still a quantitative variable, and ideally it's going to be a quantitative variable that's symmetrically distributed and maybe close to normally distributed. You have some explanatory variables. In this case, you have more than one, and you want to be able to identify the relative contributions of each of these different variables to explaining the variation in the outcome variable. So an example of a successful ANOVA with multiple factors is the A/B testing that was performed by the Obama campaign. So they had a website where they were trying to get people to sign up for the mailing list for their campaign, and so they had three different wordings that they could apply to that website: learn more, join us now, or sign up now. And they found that learn more garnered 18.6% more signups per visitor than showing visitors the other variables like the default sign up. They also showed that having a black and white photo of the Obama family improved the sign up by 13.1%. And finally, they showed that using both the family image and the Learn More increased the sign up by up to 40%. So this is actually quite a dramatic increase in their number of signups by taking advantage of the relationship between the two variables. So it's often a case where you're going to want to be able to analyze multiple variables in an ANOVA model. Since we don't actually have access to Barack Obama's campaign finance information, we are going to use the movie data from that we collected from this Rossmann Chance website previously. So again, we have the movie title, the score on Rotten Tomatoes, the rating, the genre of the movie, the box office, and the running time. And so we're going to be using the score as our outcome and then these other variables as covariates. So remember when we were doing a one-way ANOVA or an ANOVA with one variable, what we would do is we would have the score as the outcome variable, and we'd write that as a function of the rating. And so in this case, there was a set of what's called indicator functions. So these are just logical variables. So if the rating for the ith movie was equal to PG, this is equal to 1. Otherwise, it's equal to 0. Similarly, if the ith movie was PG-13, this variable was equal to 1. Otherwise, it's 0, and so forth. And so what we get here then is B0 is the average rating of the G movies, B0 plus B1 is the average rating of the PG movies, and B0 plus B2 is the average rating of the PG-13 movies, and so forth. So actually all we have in this model is one covariate. It's just this rating covariate, but it's separated into three different variables because there's three different levels of that factor. So we can perform an ANOVA in R using the AOV command, and so AOV works a lot like LM in the sense that you pass it a formula, where the formula has on the left-hand side of the tilde the outcome variable that you're interested in this case the Rotten Tomatoes score, and then a tilde, and then on the right-hand side of the tilde the covariate variables, in this case the factor variable for rating. And so then if you look at this analysis of variance object, it shows you the sum of squares for the rating and for the residuals and the degrees of freedom. So remember that the degrees of freedom in this case is the number of parameters you're estimating, so it's about 3 because there are actually 4 different levels of the movies, but one of those levels gets absorbed into the intercept term, the B0 term. And then there's 136 degrees of freedom left over for the residuals. And so that's what happens when you have a 1 degree of, or a 1 covariate model for an analysis of variance. And you can get the estimated coefficient. So for example, 67.65 is the average Rotten Tomatoes rating for a G movie. 67.65 minus 12.59 is the average rating for a PG movie, and so forth. But you might be interested in adding a second factor to your model and seeing what the relative contribution of these two factors is to the score. And so here we again have an intercept term B0, but now we have the same rating variables that we had before. So we have a level for PG, a level for PG-13, and a level for R. But now we've added a second variable, and this is for the genre. And so the genre is actually many more levels than just 2. So I've put this ... here to indicate that there would be many more of these variables here. But now I have a coefficient gamma 1 times an indicator that it's an action movie, and this works just the same way, where the ith movie, if it's an action movie, then this is equal to 1, and otherwise it's equal to 0. And here again, if the ith movie is an animated movie, this is equal to 1, otherwise it's equal to 0. And so we've added this second set of terms to the model, and so that's actually only a second variable. So what we have here actually is two variables with multiple levels. So the rating variable has these three different levels that we saw before in the one-way ANOVA. And then once we've added a second variable, it actually has multiple levels as well. So it looks like we've included a whole bunch of new variables in our model where it's actually just the two variables because they're sort of clustered together by the factors that they are for specific variables. So you can add a second variable very easily in ANOVA and R. What you do is, again, you have the left-hand side is the outcome, a tilde, and then if you want to have multiple variables, you can just concatenate them together like this with a plus sign in between them. And so you end up with movies rating here and movie genre. These are both factor variables. And if you look at this an analysis of variance, now you see that there are 3 degrees of freedom that are used up by the movies rating because we estimate those 3 different levels. And then for the genre, you actually have 12 different degrees of freedom that you're using because there are actually a larger number of genres than there are ratings. You get more degrees of freedom that you're using up. And then at the end, you are left with 124 now degrees of freedom for the residuals that you're going to be using for performing your inference. So what you can do is you can actually look at a summary of this object, and what it'll do is it'll tell you, again, a lot of the same information, the degrees of freedom, the sum of squares, and the mean square, and then it'll also give you the F value. So the F value here is the F value for the variation, the first F value, the variable that comes first. This is for it measures the amount of variation explained by rating in the score variable, not taking into account anything else, and it's p-value. So again, remember p-values, if there's nothing going on, are between 0 and 1 uniformly. And p-values less than 0.05 are generally considered to be significant, so here we don't necessarily see anything going on. And then the genre variable it has an F value as well, but this F value now is interpreted a little bit differently in the sense that since it's the second variable that's included in the model, this is the additional variation this is measuring the additional variation that genre explains that rating didn't explain already. And so this variable you can see actually is a little bit closer to statistical significance and has a little bit larger F value. But this is the F value that you get with rating already included in the model. So an important thing to keep in mind is that unless you have a balanced design, the order of the variables actually matters. So if we look at a second version of this analysis of variance where it's the exact same thing, we have score on the left-hand side, the tilde, but now we've just flipped the position of rating and genre. So genre comes first and rating comes second. You can see that you get a different F value for genre and a different P value, and same thing for rating. And the reason why is now this F value corresponds to the variation in the Rotten Tomatoes score that is explained by genre without taking into account any other variables. And this F value is quantifying the amount of variation explained by rating after taking into account genre. So you can see in this case you get slightly more closer to significance for genre than you do for rating than you did in the original AOV object, which I've shown you here below. So you get different p-values, different f-values than you do when you switch the order. So the order matters particularly if you have what's called an unbalanced design. In other words, if the levels of the genre variable aren't exactly distributed evenly between the levels of the movie's rating variable, you will see differences in all of the statistics. And so you have to have some care in interpreting what percentage of variation you're explaining. Are you explaining percentage of variation not taking into account anything else, or percentage of variation already accounting for some other variables? You can also add quantitative variables to this ANOVA model. So again, this is the same ANOVA model where we have the Rotten Tomatoes score as the outcome, we have the movie rating terms, we have the genre terms, and then I add just a quantitative variable for the box office here. So the box office is just a number in millions of dollars. And so you actually just include this as one more term in the model. And so since this isn't a factor variable, this is actually a quantitative variable, we only include it as one term. And the important thing here is that when we include a factor variable like this, the difference between an action movie and an animated movie doesn't have to be the same because gamma 1 and gamma 2 might be different. When we include it as a quantitative variable, what this is saying is if I increase the box office score, box office amount by $1 million, I will increase by 8 to 1. If I increase by a separate $1 million, from 10 million to 11 million is the same as from 11 million to 12 million and so forth. So we're basically constraining all the 1 unit differences to be the same when we include it as a continuous variable here. So it's interpreted and it's analyzed a little bit differently. And you can see that in the ANOVA table. So again, we've created an ANOVA object here where the score is the outcome. We have the genre variable, the rating variable, and then the box office variable. And if you look at this, you can see that only 1 degree of freedom is used for the box office variable because we're constraining all the 1 unit differences to be the same. So we only have one eta, one parameter for that. And so we can actually, use up less information to estimate it, but it means that the parameter that we have for box office is somewhat constrained. Unlike for genre or movie rating, where the difference between a G and a PG movie could be totally different than a PG and a PG-13 movie, for rating, and that's why you would see more degrees of freedom being used for the parameter estimates, but you allow for more flexibility. So a little bit about the language for ANOVA. So a unit is a one observation in ANOVA. You often hear the word unit used in ANOVA. The treatments are the different conditions that the experimenter applies to the different units in the study. The factors are what are controlled by experimenters. So these are the conditions that maybe they are not necessarily of interest. They might be technical conditions that are just being controlled by the experimenters but aren't necessarily part of what's being sort of tested for interest. And then their replicates are multiple, usually independent units with the same factors and treatments. So to use this ANOVA well, you're going to want to have leftover degrees of freedom for the residuals after you fit all your parameters. So you're going to, in the example of the movies data set, what you want to be able to do is say have more than one PG movie. So once we estimate the average for the PG movies, we can see what the variation is around that average and use it to perform statistical inference. I've linked here to some Wikipedia articles that actually do a really good job of explaining experimental design, ANOVA, and A/B testing, like the example I talked about with Barack Obama. But any reference on ANOVA or linear models is actually quite good. This is an area that's very, very well studied and very, very well taught by a lot of different people.